So first, thank the organizers for the invitation. This is where I graduated, so it's very nice to come back always. Also, I want to apologize to the audience in the sense that this talk does not have too much, so far, direct connection to biology, but I do think it can be, it has been used to model epidemics, crowd motion, and I think also could be in the future, hopefully, or probably people are doing now to model by agents, their behavior, their dynamics. So that's the future plan. But the good part is, since we're in Southern California, I think talking about traffic is very appropriate. So I will use traffic models as examples for the motivation and for this formulation. The good part is you can sit back and relax. You don't need to fasten your seatbelt. Absolutely, there's no danger or controversies in this mathematical talk.
You never know.
You never know, okay. For mine, yes. But of course, I hope, the even better part is most of you do not have to navigate through Southern California traffic, except Natasha, Dominic, Ruth, Tom. So hopefully some of this discovery here could help in the future when you navigate through heavy traffic. Okay, so this talk is, the title is here, it's kind of strategies for mean field games. I will introduce the mean field games in the next slide. And this is a joint work with my postdoc, who of course did most of the work, and my colleagues, Xiuyuan Chen and Jianguo Liu at Duke Math Department. Okay, so what is the mean field game? So let's just thinking the drivers, commuters, are those players. So usually, so the two crucial things is non-cooperative. So when you plan your path from, say, Irvine to San Diego, you probably don't talk to many other commuters. So, and there are a lot of players, and they're indistinguishable. They just want to go from place A to place B in the fastest way or least stressful way. So it's non-cooperative and a continuum, a lot of indistinguishable players. Okay, so this is spatial domain. This is the time. So you're thinking about navigate through some space domain, and this time 0 to t. Again, each individual makes decision based on, there are interactions, but the interaction depends on through an optimal control work. So, and the interaction is very interesting. It's not the cooperation, but it's mean field behavior. So basically, the traffic density is something affect your decision. So okay, so that is through the distribution. So you definitely try to avoid the heavy traffic route. So that's what the mean field is about, is the distribution of the players that interact your things. But given this mean field, the current distribution is becoming, for each individual, is just optimal control problem. Okay, consider these things. Okay, so let me to mention the notation. So very straightforward. This is a density of the population at time t and location x. Okay, that will be mean field. And strategy is how you control your velocity, which route you take. Or many times we use these two instead of these two straightforward variables. Usually we use the density and the momentum, or the flux, rho times v. Okay, so these are our variables, and the cost is your travel cost may depends speed, may depends on the road condition. Okay, so but we assume it's convex in this velocity variable. And interaction, this is really interaction cost. So for example, maybe your cost growing quadratically with the traffic density, okay? So this is this. And well, these are auxiliary variables. When we talk about Lagrangian, you talk about this convex conjugate around the transform, Hamiltonian. Value function, this is very important. It has two meanings. In optimization, you can think of it's some Lagrange multiplier function to enforce some constraint, but it does have a concrete meaning, cost function. So when you're at point X and T, when you reach time T, what's the cost? Okay, so it's a little bit backward. It's going backward in time. So you see when you're further away from capital T, what's the cost if you are at location X? Okay. So this model was first introduced by these people, and it has been quite attract a lot of interest, because when you have many players, you definitely cannot use to track each individual one because it's too costly. So they introduced this model, and they used to now model some economic behavior, crowd motion, epidemics, now also reinforced learning in machine learning, things like that. Oh, also please interrupt me if you have questions. Yeah. As I said, also, just like driving, right? I'm the driver, so I don't get car sick, but usually the the passengers get car sick. So please, yes.
To understand, when you say mean field, you mean what physicists mean by mean field? So not thermodynamic limit, but something in between?
Yeah, when the number of player goes to infinity, you have some distribution. You use the continuous distribution to describe how these players' density, things like that. So that's called mean field. Okay. You can call it empirical density when it goes to infinity. It's give you these things. Okay, so the mathematical formulation is quite straightforward. Given population, so the very important things, imagine, right, Natasha, when you try to plan tomorrow's commute from Irvine to San Diego, one thing is you listen to the radio about traffic situation today. Maybe 4 or 5 is always jammed. Then you try to take a different route. So the thing is, let's make it relatively simple in the sense, the only part that is different from optimal control for each single player, which is well studied, well understood, is to incorporate the interaction cost, which is only depends on the current distribution. So say today's, the traffic, and tomorrow you plan according to this, okay? That's the things. And this is usually the travel, there's always some noise, and there's the velocity you drive, and this is something you can control, and you try to minimize this. The goal is not for each individual, but as a population, what's the expected cost, okay? And variation formulation, you don't need to take this. You just have to track the probability density, or the density evolves according to this rule, right? This is conservation, and this is due to this Brownian motion, but without this is purely conservation of math, okay? So your initially what are the people's, how many people, where they live at different places in Irvine, and then you try to, give you this initial distribution, and you want to evolve this, design the V and minimize these two variable, but the rho is definitely evolved according to this, and this is equivalent to that one.
So that's a Fokker-Planck equation, right?
Yes, yeah. Absolutely.
Can you please again define rho tilde?
Rho tilde here, I'm going to describe what is the Nash equilibrium. So right now, as I said, usually what we do is knowing what's the current distribution, find the best response to the current distribution. But of course, if everybody do in the logical way, essentially it will goes to some, did I say in the next? Okay, still, okay, so a still formulation in the next slide, we'll talk about were the definition of Nash equilibrium, which we aim to find. Okay, so so again, if you think the variational problem is like this, okay, again, the rho tilde is unknown, so the only thing is rho and m. Now you see I already used this new variable because very interesting mathematically, but in practice it doesn't really solve the problem yet, numerically especially, is after you do the change of variable, this is a convex functional in rho and m, even in this form, because the convex in this is convex in rho and m, and the constraint become a linear constraint. So the whole things become a convex optimization problem. Mathematically, you like it much better than the previous version. So you do have this. So this linear constraint. So that's one thing, many computation or study based on this model, but we'll find out where this may not be as good as the following model. If you derive the Euler-Lagrange equation introducing the Lagrange multiplier function for this constraint, which is phi, you will have a Hamilton-Jacobi equation. Okay, so the phi, either you think of it the Lagrange multiplier function, or this has real meaning. That's the cost function at x and t at any location. So if you solve this, you know what's the cost at any location x and t when you reach time capital T. And this is just the Fokker-Planck, and actually the v is equal to this. Okay, so it's become a partial differential two partial differential equations. One is the Hamilton-Jacobi equation. The other one is Fokker-Planck equation. But they are coupled. They're coupled. So, for example, the phi hat is used here. Okay, but more importantly, if you look at each individual equation, is a time evolution dynamics. It's very easy to solve. You're just starting from time t is 0, marching time, numerically it's easy, and it's equal to 2. But here you see, oh, I forgot, this is terminal cost. For example, you have parking lots at different locations, they have different prices. You definitely, you need to take out where you reach the end, where you should reach when capital time t. So this is exit cost, exit time cost. So you see the cost function is going backward. You know the cost at capital time t, and you try to evolve backward to see at earlier time what's the cost at the location at the earlier time. And this is telling you the evolve of the population, which you know initially, the distribution of people in Irvine and how it evolves according to this dynamic. So it's a two boundary value problem. Okay, if each one is easy to solve, but when you couple them, it's not, because one is given boundary condition at this other one at t0. Okay.
So the only thing that differs from one problem to another is your choice of the cost function, right? The structure of the equation is always the same.
Yeah, the structure equation is the same. Only things, yeah, if you put the rho 0 in there, you put the particular Lagrange in there, this is h, everything is determined by this system. And the phi is according to, given the current population density, what's the value function? And you take the gradient, you take the gradient, put in h, take derivative, you got the velocity. What's the control? Okay, this is the Lagrangian formulation. This is all. This is Lagrangian formulation is Eulerian. Everything here is only defined in space x and time t. Okay, but it's going up other way around. They're coupled, and this is one is nonlinear. So this is things. Okay, so the Nash equilibrium. So the thing is, whether there is a distribution, you know, when people behave in a good way, here we will tell what is good way is. It's not very complicated. It just means somebody has to compromise. People need to compromise. You cannot everybody try to take advantage, always going the best. And if you have that, then there is a hope you can go into an equilibrium state where the expected or average cost is the lowest for the whole population. And is this basically, if you fall, there's a density distribution. When you're using that to design your optimal path and see how the population goes, the population density doesn't change anymore. Okay, so everybody can do a plan according to this population density, but if everybody does what those individual optimization they do, eventually you don't change the population density anymore. And the cost also doesn't change anymore, the stationary. Okay, so that's the things. We're trying to find what this fixed point is.
So wouldn't the Nash equilibrium be the solution when you drop the time derivatives of that second
No,
equation?
it's not. There's a state, you see? The previous one, I have rho tilde, then I minimize this, get rho hat and m hat, okay? But if I put that rho in, this rho will be exactly that rho, minimize this. You're not changing the density anymore. You reach the equilibrium. So everybody still try to optimize their own cost function, but the whole population density doesn't change anymore. So it's reached equilibrium, yes?
What do you mean by best response?
Best response is basically, you know the current, well, we all know, right? We listen to the traffic radio, and given this one, we design our route. Okay, that's best response to the current mean field. Okay, but if the best response will recover, won't change the density, then that's you reach the equilibrium. Okay, yes?
So you're only looking for existence of equilibrium, but not whether you would achieve the equilibrium given an arbitrary.
Yes, I think they are both important. There's one study is whether exists such equilibrium. And the next thing is, if there is, how do you find? And many times, sometimes the equilibrium may not be unique. Can you find one? Okay, so here we try to say some simple mechanism will guarantee you, if there is a Nash equilibrium, goes to there, and also that's going to drive our computational algorithm, how to achieve that.
So you said goes to there. If you have the Nash equilibrium, do you know that that's going to be stable with respect to?
Yeah, I think that there are some assumptions about. I'll talk to you. Those things will guarantee the stability, uniqueness of this. But in general, this is a lot of other open questions. Yeah. So I think also we're talking about inverse equilibrium. So say things started when things reach equilibrium by some measurement, can you infer some interaction cost or the environmental potential, all those kind of landscape, those kind of things. I think that's definitely more interesting in practice. It's just by some measurement of people's cost. After some time, relaxation time, can you infer what's the landscape? If you have some non-intrusive environment, right? You put some agents in there, you control their interaction, and you can measure when they return, what's the cost? Can you? But that's the second part. Hopefully I will get there. Okay, so, but it's, as I said, in order to solve this, coupled equation, it's not only coupled, but it's two boundary value problem. So it's definitely much more complicated than solving one of them. Okay, so, well, the very aggressive, we call it revolution decision is basically say, right when you go in the traffic, you hear there's a jam in 405, they tell you a different route. Most people, hopefully not all people, will just go to that route. Then what do you find? You find you get jammed in our new route, right? So it's definitely, this is a very aggressive approach. You know, given the current situation, you just make your decision based on just current decision and try to optimize all these things, okay?
It's because everybody has the same information, so they follow.
Yes, you can think that. Yeah, exactly. And also it's this aggressive, you don't regard some relaxation or averaging, especially with the past, right? When we talk about the wiser person is not just based on his decision on next day based on today, but also on the history. Maybe 4 or 5 is usually more jammed than 5, then you definitely put some weight in that consideration, right? Not just based on the current situation. Yeah. So, but the simple one or simple fixed point iteration is just every time given this, you optimize your choice, your decision, and that gives you a new distribution, and you try to iterate. And may not converge. I give you a very simple example. So this is San Diego, this is Irvine. You have two equal route, exactly the same, make it seem simpler. And today, if you hear the traffic today, there's 60% goes to this route and 40% goes to this route. Okay, everybody, when they return, try to plan for tomorrow's. Well, they know it's slower here. Okay, it costs more. So this, they don't change because they say, I'm going the right route. And this, all of them, well, if I do this, a strategy, the 6% will go there. So immediately tomorrow, 100% people will go through this and 0%. And then the next day, this 100% go here and 0. So you just oscillate. You never reach the equilibrium. And even when you have 50.0001, this is 49.999, you still do the same. So even small perturbation, that's a kind of unstable. You do this, then you will go back to this. Okay? So what is the strategy? That's what shows numerically, even you start from equilibrium, because numerically there's round-off error, and then immediately goes down to oscillatory state. So what would you think would be a good or simple fix for this? Randomize, close. Not everybody, evolution. So in a sense, some people has to be compromised, less aggressive, so there's only certain percentage will follow the aggressive one. Most of people, so maybe next time when you hear there's traffic here, but nowadays GPS always prompt you a new route, right? Even 2 minutes difference that tells you, would you choose this one instead of the original one? So next time, be a little bit more conservative. So don't always pick the better one, and that will help, just not everybody. And the thing is, actually this delta K plays an important role in how fast they converge. If you're too aggressive, that's difficult, but you're too conservative, that also slows down the convergence. And you can imagine in this very delicate situation, these people, the percentage who's taking the aggressive approach should be extremely small, okay? So that you don't have a big population go there because you only need to do a little bit adjustment near the equilibrium. So when closely cooked, so here is the things. The only thing you need to change, instead of choosing this one, you give some weight average between your old one, today's decision. Some people stick on, most people, I say most time, you should, depends on how far away your equilibrium, but basically a portion stick to the old strategy, a little portion change to the totally a new strategy. If you do that, kind of relaxation, averaging, history, there's memory of history put in there, you will better. Okay, so yeah, that's the called fictitious play. Yeah, in the old days, mainly they proved for this potential game field, which means the total things has a variational formulation. But here, for the first time, we can show that for the non-potential game, by designing the right Lyapunov function, it shows still this strategy can be effective. So, okay, so that's the very important Lyapunov function to monitor this dynamics.
So 1 second, what is the result then? So if only delta percentage of people follow the best strategy.
Yeah, first of all, you have to do this. The second thing, you have to choose delta K smartly with K. Okay, delta K, you cannot, well, you can. There is some fixed scheduling about the delta K, but we can show you can better design this to make it converge faster.
To the equilibrium. That you converge to
the equilibrium faster.
But you have to choose the delta cleverly.
To make it faster. There are fixed ones. Guarantee you can convert.
Any delta less than 1 will get you there.
No, delta K has decay with some of delta K needs to go to infinity.
What is K? Sorry.
Excuse me?
What is K? Delta K?
The K, the iteration. The number of days, today, tomorrow, the K, whatever the iteration. This K is just iteration. Every time this is your current, next time you do this. Okay. Yes.
since you involved evolution, wouldn't it be easier?
Excuse me?
Wouldn't it be easier if you just say, I copy those who are successful, because then you don't have to do all this calculation. You could calculate the travel times of everybody and then say with a certain probability,
non-cooperative. You don't talk to other people. You only know the distribution, but you don't know who are successful, who are not successful. So here is a non-cooperative. So there's no organization. If you know that information, of course, you can even control it different way. Here you don't know who are successful.
But I know the distribution of traffic on, say, both roads, right?
Yeah, but but many of them are the victims. They're not successful.
Yes, but with this distribution, I could calculate the travel time on both roads.
You don't have that information. Each individual's, okay, so when you do optimal control, you only know is today's traffic, how you plan tomorrow's traffic. You only know today's traffic situation, how do you plan tomorrow's. You don't know how many of them are going through the better ways, how many of them go to the bad ways, but all you know is today traffic on 405 is heavy, traffic, the traffic in 5, I assume we go those two routes, is less traffic. That's all you know. Like ambient information based on today's current distribution. So as I said, I mean, you can put biological agents go inside. They don't really communicate. You don't know who's doing what. So in that sense, it's smart agent, but not too smart agent or too much information you know about this. Okay. Okay. So where okay, I think it's here. Yeah. So this is basically just remind you. Okay. Oh, this is the gain function. Okay, very important. Okay, so here again, follow up what we just discussed. This is the current situation, population density. So it's a given information, and it's just become an optimization. Okay, the cost function is just function of m rho, and most important things is here the nonlinear one is given, and only is a linear in rho in this one, okay? The same thing here. And then you define this, if given the current one, I optimize the best response, okay, to do this, see how much I can gain, okay? So the thing is, given the current one, now everybody design, you can use computer simulation, if you all know the Lagrangian, you know the row tutor today's traffic, you can definitely optimize this. So one way to see how close we're going to show something computable in practice is just to observe what you can gain by optimize this with this current best response to this current population density. If you do that, if you can still room to improve, that's really that room to improve we're going to show tells you how close you're to the equilibrium. As long as the room to improve, you're not there. But when this room of improvement becomes smaller and smaller, you're closer and closer to the Nash equilibrium. This is totally computable, and yeah, from your current situation. So that what we're going to show, we show that this gain function is really telling you how far you are away from equilibrium distribution, and also it's equivalent to the distance from your current one to the best response. So all these are equivalent. Okay, this is also compute. Yesterday's traffic, today's traffic, the difference of this is equivalent to the gain things, and also that tells you how far away you're from the true equilibrium. Okay, so all these are equivalent. That's what we can show. And if you choose delta k properly, this can decay exponentially or linear convergence. Most time people can only get sublinear convergence if you have a fixed delta k scheme. Okay, so well, this is some assumption one, but let me emphasize okay, these things. This is very crucial for the existence uniqueness of equilibrium. It's called monotonicity of the interaction function. Basically saying your cost always increase when the density become larger. You're monotone in terms of the density, right? When you have more traffic, definitely the cost bigger. You can now sometime favor you, sometime it's not in favor of you. So this is the monotonicity to make the game actually is much controllable. Yeah, some people call it socialism. Everybody's just trying to boost the society together in the same way. Okay, this is just general Lipschitz, that's nothing new. And there are some extra, for theoretical proof, we still need some technical assumption, basically saying there's some convexity of the, a strong convexity. We know it's a convex, but we need some strong convexity in this cost function in order to prove what we do. Okay, okay. So the very important thing, it's a very simple, but it's a very important thing to give you the direct intuition why you need to do average. Is basically saying the following. Remember from monotonicity, we said this is bigger than 0, okay? But if you do the optimization, we can show you go to negative, so which means you're over-aggressive, you are reaching to the other part. So for example, let's say this. So if this is the direction of this one, is in function space, of course, this vector in function space, and initially you're here, the difference here and difference here on the opposite side. So which means if you do some average, you're closer to this. You're always over. When you do the aggressive one, you know you're going to be. Mathematically, this is a rigorous way of saying you're always over to jump to the other side. So if you don't do relaxation, you may jump from this side to that side, this side to this side. But here, if you do relaxation, you're always going to be better, close to this. Well, I think this is, yeah, I said this is the, I think that the thing is the gain of the best response is our crucial quantity to judge how far, can really tell you how far you're from the equilibrium. Yeah, so basically, again, without noticing the details, we can show that this one is a kind of Lyapunov function. It's always decreasing if you choose the delta k properly, which I'm going to show you. And then also it's equivalent. It can tell you everything you would like to know how far you are away from equilibrium. Again, as I said, the gain function is saying, if I know today's traffic, when I do optimization based on that, do I still have improvement gain? If you have, that means you're not here, but the gain is small, that means you're close to equilibrium. Okay, so this is how we can show how this is how convergence determined by the choice of delta k. Okay, so basically there's a competition by, you definitely want delta k to be large enough so that this balance is due. But this showing there are always a choice of delta k. When it's small enough, you're going to improve. Okay, because this is depends on delta k squared. This is minus delta k. So delta k cannot be too large. When it's too large, this will dominate, and there's a constant, we'll see what it is. And this will be better than that, you're not converging. Okay, so there's definitely a small delta k, you're safe. But of course, you want to maximize this to make the contraction. Okay, so we have the things, and everything is explicit. This C depends on that. All those constants we introduced before. So if you know the C, you can definitely choose the best delta K. Okay. So if you know C, then you just choose even constant one. But you have, but this is the global constant. Okay. If you have a global constant, you can show it can be always exponentially decay. But in practice, this is not globally bounded away from 0. So you have to, especially when you're getting closer to equilibrium, the C become larger and larger. So you need to choose delta K to be smaller to make sure it's still converging. You're contracting. Okay. Of course, numerically, we have some more practice because you don't know what that C is and how C changes in iteration. So here we have some backtracking line search, like when we do optimization, to choose more appropriate delta K to make the convergence faster. This is a numerical trick. After we know what's going on here, yeah, so there we just have to do it more numerically in practice. Okay, that's the algorithm. The most important things for the fictitious play, why it's simple, efficient, because originally, at the equilibrium state, those two time-dependent PDE are coupled, and one from 0 to capital T, and this one is from capital T to 0, two boundary value problem. But now we're becoming two separate systems. Every time I have to simulate just one system, this is from capital T to 0, and I put that information into here. I only to simulate the second equation from T equal to 0 to capital T. So instead of coupled, now it's like a shooting method, it's become decoupled. You don't have to couple them together. Numerically, mathematically, that simplifies a lot when you really try to do some calculation. Okay. The other thing is, of course, computational people is always thinking how you can improve this. When you have two boundary value problems, so it's really difficult. The most important thing is to propagate the boundary conditions quickly inside to balance. So one way to accelerate that propagation is using coarse grid. So you get a coarse balance, but you propagate the boundary condition much faster to the interior domain than using a fine grid. Okay? So you use coarse grid to give you a rough balance, but boundary condition effect is propagating quickly, give you a good initial guess. You put it on a fine grid, you do that, and you do this kind of things. Then you can accelerate this thing. There's a subtle things, of course. When you don't have viscosity or this Brownian motion, this is hyperbolic. You can have singularities. So it's much harder to compute numerically. Usually numerically, we have some numerical viscosity. Numerical viscosity usually is proportional to the grid size. So I'm use a much more smooth version on coarse grid, and then automatically adjust it to a more hyperbolic version on the fine grid. Okay, so that's all numerical. So things we can show you that if you choose delta K small enough, it converges exponentially. And if you choose too aggressive, delta K equal to 1, this is a fixed point iteration, you see it doesn't converge. Although the thing you have to look at the label here, this is 0.08, this is 0.16, but here is 10 to the minus 10, something like that. And this is show you the angle between this one and the optimal, the best response, they're negative. So you're jumping away, you're overshooting. And this is showing a backline train. So if, in general, if you choose too aggressively, you're not converging. If you choose 0.1, it's okay. And this is usually a fixed strategy. Their delta K is 1 over K plus 1. So it's decaying. It's decaying, but it's fixed and it's slow. But if you do the adaptive one, it's backline tracking, it's much faster. And here is more kind of transport. Basically, you want to move, okay, maybe this is on a fine grid, move a bunch of agents or players to this location, but there's obstacle, there's maybe bad road condition here. People need to always avoid that. And what's the best way to go? Okay, so this is using hierarchical grids. And quickly you see this split into two, go around this obstacle in between, and converging here. This can be used, accelerated using hierarchical grid. Okay, here is saying, okay, there is one special case of mean field game. This interaction cost, terminal cost, is derivative of some potential. So which means the whole problem, I want to ignore some mathematics, saying the whole problem is just characterized by this variational problem. Okay, so as I said, when we do the change of variable for the people doing optimization, they're really, really happy. this is just convex optimization. Looks everything is rosy, but actually nowadays I'm not expert for optimization. If I'm biased, maybe this is the part you need to fasten your seatbelt. I think when you have a large, okay, let's see what's wrong with this optimization, right? So what you do, you put all these unknowns, m and rho, in the whole space and time, lay down the grids in space and time, huge number of unknowns, it's all coupled, and very unlikely you can use Newton's method, you have to use gradient-based method. And the worst part, I mean, gradient method is always you can use, right? I'm not even worrying about you go to local minimum and the global minimum because it's a convex things. But gradient descent method is very sensitive to conditioning of the Hessian. And most of the time when you're dealing with differential equations, dealing with this change of variable, where is m over rho, when rho is small, this dependent on, at those points, this dependence is very, very strongly, but for rho is large, there's all this large L is very large if rho is small, and also differential operator, it's not a compact operator. All these things can cause, and you put all these grid points in there, every grid point is the same, you're using a gradient descent, it's very, very inefficient, very hard to do. So although there's a large coupled discrete system in space and time without utilizing any underlying physical structure, geometric structure, whatever, information, ill conditioning due to differential operator, and also this change of variable causes really challenge to do this using gradient descent-based method. Well, if you look at our best response, the number of iterations independent of grid size, because it's governed by the whole converging mechanism, is in a continuous sense, it doesn't depend on the grid size, but here it does, because when you discretize grid derivative, you have to divide by the grid size. Can handle rho equal to 0? Doesn't matter. Can be accelerated? Yeah, so this. Okay, so how many minutes do I have? Okay, yeah, I won't go over more than 6. Okay. This is, I think, is interesting, although it's just a recently started project. It's saying, the idea is the following. So, okay, so let's say I'm trying to explore some terrain, non-invasive one. So I put in a bunch of drones or some agents, could be biomarkers into there. Their dynamic cost, you want to minimize the use of battery for sure. And they are influenced by the ambient environment. I call it potential. Some road condition is good, some road condition is bad, somewhere is hilly, somewhere is flat. So that is reflected here. You give the drone some simple interaction cost. You definitely don't want them to congregate. You want them to be apart to fully explore the whole domain. So this is something you can control and set up. This is something you know, and this is something you want to know. So in the forward problem is basically say given Q, how do you find the equilibrium state? Okay, given Q, solve this for rho phi. That's what I talked just now. But now we want to inverse. So if after this drone come back, I measure how much energy used, how long time it takes, well, that is exactly what you measure. The cost value function or cost function from t equal to 0 when, until they exit. This is something you can measure. And then you want to infer the terrain, the landscape. Okay, so that's the inverse things. You could see where there's a tumor tissue. I'm just making it up. Maybe there's a stronger interaction somewhere with the ambient and so on and so forth. Okay, so then again, in the old days, people just put the least square problem and using optimization to solve that. I think it's, again, you ignore. The good thing about optimization, you can always put something there. You can always try to using computation to gain something. But whether it's efficient, whether you have, my basic suggestion is you simplify to the point you have no way to do by you, then you do optimization. Not begin to set up a big optimization problem and solve it, because many times that's really inefficient. So here again, we don't do it in the least square sense. We do a simple iteration. I don't have time to tell, and also I think At this time, you're probably already car sick. So again, you do very simple iteration things, you can really effectively find, if our model is the real model you are trying to solve, you can really do quick convergence. Just a few iterations, you can get a very good estimate about the true one. Okay, this is the first iteration. This is after 23 iteration. You don't see any difference. Yeah, this is the logo for Blue Devils. If you watch basketball, you probably see them a lot. And then this is our background. You can see you can recover after 18 iteration in 2D. And you can do many acceleration numerically. These things I don't want to talk too much, but let me conclude by saying we first derive a simple mechanism to say how it affects the convergence based on a very simple strategy, fictitious play. Basically, you do an average between today's information and the calculated best response you are going to do. Not always take the best response, okay? If you do it correctly, then you will help the whole population reach the most efficient state. We show the gain function. That's the crucial thing in our proof, in our show, is this construction of the gain function, which is the Lyapunov function. We develop, based on this understanding, efficient iterative ways to solve it numerically. And also we, using this, develop for a class of inverse mean field games. You can use that to explore the terrain, the landscape, in a non-intrusive way. Yeah, again, that's the things I maybe mentioned a few times. Generic optimizing formulation algorithm looks powerful, but looks convenient to use, not powerful, looks convenient to use, but usually they're not necessary. Usually far from a good choice. Maybe it's the only choice, but hopefully it's not the only choice. Yeah, here is our publication, some published, some is on the archive. If you're more interested in detail, you can definitely find it. Thank you for your attention.